let's go ahead and do some examples of finding antiderivatives and integrals of various functions. I'm going to start with problem 14. They're asking us to integrate 3t to the fourth dt. I guess the first thing that we can notice here is that we're not using x, we're using t's. But the variable itself doesn't really matter too much. So we'll just treat this the same way as we were doing before. First thing we do is notice that the 3 doesn't really matter. We can even go ahead and just pull it out if we want to. The next thing, we use our power rule for t to the fourth. Remember how that goes. We take our power, we increase it by 1, and then that new power we divide out in front. Remember that plus c at the end too. I'm going to go ahead and just rewrite this as 3 over 5 times t to the fifth power. And it's really just that simple, at least for a power it is. Now, don't forget that plus c at the end. If GeoGebra will take off points if they are expecting it. Some of their problems, they'll actually put the plus c behind the box and they're just looking for the function itself. But if they don't have that, you're going to need to put it in there. Also, on the final, when I'm asking you problems about indefinite integrals, you're going to need that plus c, or I will be taking off points there as well. Do not forget the plus c. It's important. Basically here, we have a full family of functions, an infinite family of functions, all given by different values of c. And there are definitely problems where if you don't put the plus c, you can get an answer that isn't actually correct. And even when they're kind of expecting a particular value of c in that example. We'll get into, not specifically problem spawns like that, but we'll get into places where we do need to know what that c is. Let's look at problem 17. Again, here they're using different variable, but it's the same idea. We're integrating y to the 3/2 power. Now this is just a power. We can use the power rule. Remember that power rule says that we take 3/2 and we add 1 to it for our new power. 3/2 plus 1 is 5/2. So our new power is 5/2. And you definitely do want to simplify that to just a single fraction, because now we're going to have to divide by 5/2. Or in other words, we're going to reciprocate 5/2 and multiply. The reciprocal of 5/2 is 2/5. It's better than writing 1 over 1 plus 3/2. We want to write it as one fraction so we can turn it upside down. And there's not really anything more to say about that one, but just be aware of how we actually deal with dividing by these fractions. Move on to problem 26. Here we have the integral of 5 minus x dx, which is a fairly simple function, but it doesn't actually have two terms in it. Note that the book did put parentheses around the 5 minus x. We don't actually have to do that. I like to think of the integration sign and the dx as kind of being parentheses themselves. Anything between those two things is kind of in parentheses. So I'll leave off the parentheses around my integrand unless the integral is kind of complicated. If it's pretty complicated, it might need those parentheses just to kind of draw the eyes correctly and to eliminate some confusion. But in general, I'm just going to write something like this instead as just the integral of 5 minus x dx. When we do the integration, we don't need to do this all at once. We can do it term by term. For instance, we integrate 5. Remember, this is when we integrate a constant, we just get 5 times x. You can also think of it as 5 times x to the 0th power. and then use the power rule for that. When we integrate x, now this one is a power as well. This is x to the first power. That means when we integrate x, we raise that power by 1. The first power becomes a 2, but now we need to divide by the new power. We get a 1/2 in front. The minus sign just kind of sticks around. And we get a plus c. So both of those do not look like powers to begin with, but they really are, and we use the power rule on both of them. The 5, even though it's a constant, we end up raising the power of 0 to a 1. Here, even though we don't write the power usually when it's just the first power, we raise that power to a 2. And if you don't believe me on that, remember we can always differentiate whatever answer we get here to see if we get back the original formula. If we differentiate 5x, we do get 5. If we differentiate x squared, we get 2x, but then the 1/2 makes us just a 1x. So we can always check our work pretty easily as long as we know how to differentiate. Next up is problem 31. You're going to take the integral of 3x cubed minus 6x squared plus 2. It's a more complicated polynomial, but it is a polynomial. So we can do with this what we could do on the previous ones. We take it term by term. We don't have to do it all at once. We just do each one of them separately. We don't have to worry about the power, or not the powers, the coefficients in front initially. We can just work with the x cubed, the x squared, and then the constant. The integral of x cubed, remember the power goes from 3 to 4. Then we need to divide by the new power, so we're going to divide by 4. I'll just stick the 3 up on top. Moving on, we have x squared becomes an x cubed. We raise that power by 1. We need to divide by the new power, but then we multiply by the negative 6. And we can go ahead and actually simplify that. Let's go ahead and even just write it out as a new line. We'll simplify that down to a 2. Next, the plus 2 here. Remember, when we have a constant, we just end up multiplying that by x. And then don't forget the plus c at the end. And there we go. We were able to integrate a cubic equation, or a cubic polynomial, pretty easily. The only real, if you can even say it, the only real tricky point was that we were able to simplify one of our coefficients. But even then, if you gave me this first equation, this first expression, I'd be perfectly satisfied. (35). This one's a little bit more complicated. We have the integral of 5x plus 4 divided by the cube root of x. Well, this is not just a power. It's also not a sum of powers. We have a quotient here. And we did not say anything about the quotient rule being transferred over to integration, like the summation and constant multiples and all that kind of stuff. In fact, there's not really a version of the quotient rule for integration. The chain rule and the product rule will eventually get some version of themselves, but even those will be a little trickier than they were with differentiation. In fact, more tricky that we don't even bother trying to make a rule specifically for quotients. What we can do here, though, is we can rephrase our integrand into a form that we know how to integrate. And that's going to be kind of a common thing in integration. It's not going to be quite as straightforward as it was for differentiation back in the first part of calculus. We're going to have to use a few little tricks here and there in order to do this integration. In this particular case, this is a fraction. We can split a fraction up into two pieces. We can have a 5x over the cube root of x plus 4 over the cube root of x. And then we can turn these both into powers. So now we have a sum of two things. Now we want to turn them into powers so we can actually deal with them. Note here that the cube root is the 1/3 power. In fact, I can even go ahead and just write it as a 1/3 power instead of the cube root. When I take x and divide by x to the 1/3, I get to subtract the powers. Remember here, this is x to the first power. So I have 5 times x to the 1 minus 1/3 power. 1 minus 1/3 is 2/3. Here we don't have a power on top. You could treat it as a 0th power if you wanted to. Or you can just realize that having a power on the bottom means that you have a negative power on the top. And now we just have a sum of two powers with coefficients. We can go ahead and use our power rule. For the first one, I'm just going to go ahead and write the 5 for the moment. I'm going to take my x to the 2/3 power. I'm going to raise that power by 1. And again, because it's a fraction, I do want to go ahead and simplify that fraction so that I can multiply it by the reciprocal afterwards. So 1 plus 2/3 ends up being a 5/3. And I'm going to multiply by the reciprocal. Divide by 5/3 means that I'm going to multiply by 3/5. And there's going to be some simplification you might see there. Do the same thing over here. I'm going to take x to the 1 more power, so 1 plus negative 1/3 is going to be a 2/3. I'm going to divide by 2/3, or in other words, I'm going to multiply by 3/2. Do have my plus c at the end. Don't forget that. Once we no longer have an integration sign, we need to have a plus c. Of course, we can go ahead and simplify this. The 5's cancel each other out. And over here, we can actually go ahead and cancel and get just a 2 from that 4. So we have a 3x to the 5/3. And then we have a plus 2 times 3 is 6, x to the 2/3. Plus c. Now, if you do have to actually put this back as a cube root like we originally had it, technically here, the x to the 2/3 could be pulled out of both of those. And we can even pull out a 3, I guess. Here, if we pull x to the 2/3 out of the x to the 5/3, that's going to give us an x. Here, I'm pulling out the x to the 2/3, and from the 6, I'm pulling out a 3, so I'll be left with a 2. And then x to the 2/3 is really the cube root of x squared. So if you really have to do it, that's the way we could write it in terms of cube roots. But I would probably just leave it as the previous line. This is definitely the easiest one to write down, I guess. Even if it might not be the easiest one to type into a calculator. Alright. Problem 45. This is a slightly different problem. They give us they're looking for a function, little f, but they give us the derivative of the function. But since they want us to find the actual function, little f, that they started with, they have to give us a little bit more information than this. If we were just to have this information here, we wouldn't know what particular constant is required. So they give us an additional piece of information. They tell us that f of -1 is -6. Now note, this is actually a little bit modified from what is actually in the book for problem 45. For an example's sake, I'm going to put in a -4 instead of a +4 in here. They have 3x squared plus 4. But I'm going to draw some pictures here in a moment, and it's going to make for a better picture if I put a negative there. Alright, so they're looking for a little f. The first thing we're going to do is integrate. We know what the derivative of f is, so we'll integrate that function in order to get an antiderivative. or the whole family of antiderivatives that little f could be. Here we have 3 times x squared. We know how to integrate x squared by raising that power by 1 and then dividing by that new power. So we're going to divide 3 by 3. We'll just get a 1. I'm not even going to write it out. The minus 4 that we have here, of course, constants, we just end up getting to multiply by x. So we get a minus 4x. And then we have our constant. We do not know what c is, but it's going to be one particular value. That's kind of what we're guaranteed here. And that's why we're given this piece of information. We know if we plug in -1 into this function, we're supposed to get -6. We need to find out what c makes that possible. So we go ahead and plug in -1. That means we have a -1 cubed minus 4 times -1 plus c. And that's supposed to give us a -6. This is a -1. This is a positive 4. So -1 plus 4 is a 3. 3 plus c has to equal -6. Or in other words, c is -9. So our function here, f of x, that they're looking for, is x cubed minus 4x minus 9. So note that different constants are simply controlled by the choice of one single point on the graph. This -1, -6, that is a single point on the graph. If we know even one point on our graph, we can use that to solve for our constant. So if we were to actually draw out all the antiderivatives of a function, then none of their graphs are ever going to actually intersect each other, because that one single point of intersection would have to determine which of those actual c's are actually valid for that particular function. Let's go ahead and actually draw this. Now I'm going to go ahead and, rather than draw a whole bunch of graphs because that can get a little messy, I'm just going to go ahead and make it what we call a slider. We're going to say we have constant c, it's an integer, and I guess that renamed it. Forget that it does that. We're going to let this c vary from -20 to 20. This will allow me to change the c as I go. Alright, remember we had our derivative was 3x squared minus 4, but our antiderivative for that, f of x, was equal to x cubed minus 4x plus that constant. In this particular case, since I've set c equal to 0, it's just x cubed minus 4x. And now I'm allowed to actually change my c as I go. As I look at different values of c, and I'm only looking at integer values of c, but you can kind of estimate where the other values of c could be. Notice that what happens as I change my c is that all I'm doing is moving my graph up and down. It's only changing the height that I'm putting my function. This is important because it means that at any point on our graph, the slope at that point, at that same x value, is always going to be the same. And that's why the derivative is always equal to the same thing. If I were to look at the point on our graph at x equals 2, say the point 2 comma f of 2, the slope of the tangent line at that point is always exactly the same. In fact, we know what that slope should actually be. Remember, our original function, our original derivative, was 3x squared minus 4. If we put 2 into there, we get 8. And so if we draw the line y minus f of 2 is equal to 8 times x minus 2, that is the tangent line at that point. It has a completely fixed slope of 8 that never changes, no matter how I change my c value. So it's just a matter of how high up is our graph. That's all the C is really doing. We have all these different graphs. They're all exactly the same graph. They're just moved up or down. There's not really anything different about them. And that's the entire purpose of that plus C. And once we know a particular point that it has to hit, then we know how high up our graph has to be. And so we can go ahead and solve for that C value. That's kind of important applications. Let's take, for instance, problem 66. This is a problem about projectile motion. Basically, we have an object that's being thrown. Sorry about that. We have an object that's being thrown, and we want to see what happens to it. Specifically, let's read it out. A ball is thrown upward with an initial velocity of 60 feet per second from an initial height of 16 feet. Express the height. They're going to use little s for height. This is going to be measured in feet of the ball as a function of time, t. Time is going to be measured in seconds. So they're saying that s is a function of t, and they want us to find that function. And they also want us to answer the question, how long would the ball be in the air? Now, in the past, we've actually used a formula for projectile motion, but we didn't really explain how we got it. Here, we're going to explain everything. So let's first draw a picture. So we have our ground here at s equals 0. We have an initial height of s equals 16 that we throw it from. So when time t equals 0, we're at a height of 16. That was our initial height. The ball is thrown up in the air. Technically, it's thrown directly upwards, but let's draw it a little bit off to the side so you can draw a curve instead of just a line. It's thrown up in the air, and eventually it'll come back down. And we want to know exactly how this actually occurs. We do know that when it starts off, it's moving upwards at a rate of 60 feet per second. That was our initial velocity. And we want to know how do we get the actual function? How do we actually figure out all these particular points? It's going to have to reach a particular height. How do we find out what that height is? How do we find out when it actually reaches the ground again? How do we get all that information? Now, once the ball is in the air, we're going to assume that the only force acting on the ball is gravity. Now, we actually are specifically instructed in the directions for this section to just ignore air resistance. That we could actually deal with that, but it gets a little bit more complicated if we do. We're going to assume the optimal situation where we don't have to worry about air resistance. Gravity acting on an object results in an acceleration, frequently just called the acceleration due to gravity. We're going to write that as -32. This is in feet per second squared. If we were using meters instead of feet, this would be a -9.8 meters per second squared. You've probably seen that one before as well. Now I'm writing this as the second derivative. Remember, the acceleration is a second derivative of a distance function. Height here is a distance function. So a second derivative is the acceleration of the object as it moves. The fact that the only force is the gravity results in us knowing that the acceleration is some constant value. It's this constant -32. I'm putting a negative here because the acceleration is downward. It's pulling it towards the ground. This is a very simple formula. Just comes from the formula F equals ma. If you remember that formula from physics, the force is mass times acceleration. We're assuming the ball doesn't change its mass, so a constant force of gravity results in a constant acceleration. But since this is actually a derivative, we can integrate it. Integrating it once to change it from the second derivative to the first derivative Remember, the first derivative is our velocity. This is the integral of negative 32. We're going to ignore the units here. The integral of negative 32, well, we're integrating a constant. So we just get to introduce, well, not an x, because we're integrating with respect to t and not x. So it'll be a negative 32t plus some constant. That constant is important because this constant is actually not going to be 0. There is a specific velocity function here, and we're going to have to find out what that c actually is. And we're going to use the fact that we know its initial velocity. We know at time t equals 0, it is thrown with a velocity of 60 feet per second. That means when we plug 0 in here, we should get 60. But if we plug 0 in here, then we get a negative 32t, that part's 0, but we get a c. We just get that plus c, and that c should then equal 60 in order to match the information they gave us. So our velocity function, s prime of t, is negative 32t plus 60. Now I want the height function. We'll take the fact that this is our derivative, our velocity is a derivative, and we'll integrate it again. So s of t is going to be the integral of negative 32t plus 60. Well, here, now we actually have to use our power rule. Remember, this is t to the first power, which means that we raise our t to the next power, the power of 2, but then we have to divide the negative 32 in front by 2. So negative 32 becomes a negative 16. The 60 is a constant, so we just get it to multiply by a t. And then we have another constant. So when we integrate twice, we end up having to deal with 2 different constants. Now, of course, we do need to find out what that particular value c is, because it is a particular value for this situation. And we're going to use the fact that we know the initial height was 16. That means at time t equals 0, we need to have s equals to 16. So when we plug in t equals 0, well, we have a 0 here, we have a 0 here. We're just going to get that c value, but that c value is then going to have to equal 16. So our answer here, s of t, should be negative 16t squared plus 60t plus 16. That is our function for height in terms of time. And the interesting thing here is that what did we get? We got a parabola. If you ever heard before that projectiles move in parabolic arcs, it's literally just because when we integrate a constant twice, we get a quadratic. And quadratics are parabolas, or at least their graphs are parabolas. So it's not really any mystery that if you throw a ball, and you don't have to deal with wind or anything like that, it's going to move in a parabolic arc. It's literally just because the parabola is given by a quadratic. And that's what you get when you integrate twice. Now they did have another question for us. How long will the ball be in the air? So we do want to know what value of t actually gives us a height of 0. I'm assuming here that the ball manages to fall all the way to the ground without hitting any obstacles. So for what value of t do we get s of t equals 0? When is negative 16t squared plus 60t plus 16 equal to 0. I'm going to go ahead and divide everything by negative 4. I don't like having a negative on my t squared. So if I divide by everything by negative 4, 60 is going to become a negative 15. 16 is going to be a negative 4. We're going to have to factor this thing. It actually factors pretty nicely, though it's not very obvious that it does, as t minus 4 and 4t plus 1. Notice here that t times 4t gives the 4t squared. Negative 4 times positive 1 gives us a negative 4. Then we have the outers is a 1t, and the inners are at a negative 16t. When you add those together, you get a negative 15. Negative 15t. Of course, setting this equal to 0, you get t equals 4, or t equals negative 1/4. So our answer here is 4 seconds, because negative 1/4 is before the ball was thrown. So that doesn't really count. Our formula is only valid for positive t's. So it's going to take 4 seconds for the ball to hit the ground. But the important thing here is how we're able to start with some formula that involves a derivative, or in this case a second derivative, and we're able to use information about the situation to derive the original function. And this is not an uncommon thing to have to do, specifically because we end up with a lot of stuff in, say, physics, where we know stuff about forces. And forces are related to the acceleration, which is a derivative of velocity, which itself is a derivative of distance. And so we end up with all these situations where we know stuff about derivatives, and we want to use that information to know stuff about the original function. We've even seen a similar thing like that before when we talked about exponential growth, where we knew stuff about the derivative, and it was a little bit more complicated, but we were able to find out stuff about the original function. Here, it's just a little bit more direct. We know specifically the derivative is some expression in terms of t. In this particular case, at least, is in terms of t, and we wanted to find out that original function. So, in a way, you could say these are differential equations, though we're just taking integrals is what we're doing. But once we get a good handle on how integration works, it will give us a lot of tools to be able to deal with any sort of problem of this kind of sort. And so that's what we're going to try to do for the rest of this course, really. Though we will take kind of a slight detour. Don't want to really get into it too much, but we'll be talking about what we call definite integrals. And we'll have to change our perspective a little bit for those. So next time we will get into kind of the counterpart of the chain rule, because that will allow us to tackle a lot more functions when we do integration. We won't get into the counterpart of the product rule until next chapter. That will be in a couple weeks. So I'll see you guys next time for our version of the chain rule.